Okay, can you see now?
Good, great.
Okay, apparently it moves from screen 1 to screen 3. I don't know why it happens. Okay, today basically I will focus on structural equation modeling because many people, about 20 years ago, not many people were using it because it was really hard to use it. You have to write the code, but now there are lots of softwares, basically click and a point type of things. So it's very easy to use them, like SPSS. Anyone can run anything on SPSS, but the problem is understanding what you are doing. Many people, I mean, I am editor-in-chief of Journal of Hospitality Marketing Management. I mean, our impact factor is almost 10, 9.8. Our scope score last year, it was 12.1, but this year so far, even the half of the year is gone, is 12.9, and it's getting higher and higher. In the hospitality, currently we are #2 journal, and we are a new comer. In tourism, I think when you combine tourism and hospitality together, I think we are #5 or #6, something like that. It's a Q1 journal, SSCI, and also the same thing with the Scopus. And I mean, we publish about 40 papers a year, a whole year. And then our acceptance rate is about 7%.
7%? Huh.
Yeah, 7%, yeah. I mean, we are very picky on what we publish, apparently. But our process is pretty fast. So we don't, I mean, we make decisions very quickly. If you go to the journal's website, you can see all the statistics on how fast the process and all the other things. I mean, we get lots of papers that use SEM, lots of them, because people think that if you use SEM, it will give you a better chance of publishing your paper. It's not true. I mean, if you are publishing, if you are doing research, it's not about the method, it's about the topic. When you do research, you're supposed to make some contribution. You need to have something unique, something new. And then you need to have a good theory. And we publish papers using a t-test in top journals. T-test. I mean, you don't need to have PhD to run t-test. And if you look at some of the marketing journals, they publish, top journals publish studies that use ANOVA or t-test. So it's not about the method. But for some reason, people in our field, they have the misconception that if you use a method like SEM, it will give you a better chance. I mean, sometimes it does, and sometimes it destroys your opportunity if you don't know what you are doing. And it's very frequently, people are not, I mean, they can run SEM, but when they run the SEM, either they use the wrong type of data, or they report the wrong things. They don't know what kind of fit indices they're supposed to report. I mean, many people don't even know what the purpose of SEM is, but they use it. So those are some of the things that we will discuss. If you look at SEM, okay, this is, we use SEM for this purpose. We look at the goodness of fit. Okay. And also we look at the validity and reliability for the measurement model, because you're supposed to go through two-step process. First, you run a confirmatory model, and then you run your SEM. And then a third step, you look at significant and a meaningful structural relationship, if there are significant and meaningful structural relationships. But the first thing you have to do, if you are using SEM, we are testing the model. First, we have to make sure that we have a good model. So we need to look at the goodness of fit. And in recent years, there are softwares that do not report goodness of fit indices. And it creates a confusion because the purpose of SEM is to come up with a model. It's a modeling tool. Okay, it's to develop models. That's the whole idea behind SEM. And test, then test the model. But if you don't have any goodness of fit indices, if you don't report them, we don't know if you have a good model. The first thing, we have to have a good model specification. And usually when you develop structural models, it needs to be developed based on theory. And many people don't pay much attention to theory. They put a whole bunch of stuff into a model, and then they run it, and they get results. I mean, if you do a study on a shoe size, okay, at IQ level, you will find the relationship. Okay, someone's shoe size and the IQ level, there will be a relationship. There will always be relationships, whether it's positive or negative. But the question is whether that relationship makes sense, whether it's based on a theory. And then you need to identify the model. Basically, that's the number of free parameters to be estimated. It needs to be less than or equal to the number of distinct values in the covariance matrix. Because your goal with SEM, you have lots of different variables in a model. You try to find which one has the most significant impact and which one has the least one. So you want to come up with a model that is small, that can explain the most. We are in social sciences. This is not like chemistry or some other science. That's why, I mean, we try to explain things, and we all come up with different estimation. So then we estimate the model, okay, based on the parameters. Then we test it. We do the model testing. We look at the fit indices. And then later, if we need to modify the model, we do the modification. But again, if we do modification, it needs to be based on theory, not based on what you think or based on the modification indices. All the softwares that utilize, and people use to run SEM, it produces a modification indices. And people modify the models, and we reject many papers because of that, without giving any justification. Sometimes they don't even tell us they modify the model, but we can figure it out. And I'll show you how we figure out. I mean, when I look at the papers, especially if they are using SEM, if what they report is accurate or reliable or not. I mean, there are several methods that we utilize. I mean, I can calculate degrees of freedom by hand for any model, because there's a formula. When you use the formula, you can calculate it. And then you can look at the degrees of freedom reported in the paper. And then you look at the number of relationships. Then sometimes you realize that people correlated things that are not supposed to be correlated, but they don't report them. And for some reason, people like to hide. So basically, model estimation, the purpose of the estimation is to generate an estimated data matrix. Basically, what we are doing is with SEM is you have the observed matrix, and then you compare to an estimated matrix. And at the end, you hope that they will be similar. Okay, there will be similar. That's why when you look at the chi-square, you don't want a significant result. You want non-significant one, saying that there is no difference between observed variance and an estimated one. Observed is the data you collect. And the software estimates that using basically it uses correlation. Okay, guys, that's the main thing with SEM. We have the observed variables, the data you collect, and then system calculates that, and then it compares the estimated variance with your observed variance and see if they are the same. And I think everyone knows how the variance is estimated based on mean, the variance from the mean score. Everything is based on those things. That's why when you submit a paper to a journal, most journals will want to see the mean scores, okay, and standard deviations. If we have the mean scores and the standard deviations, then we can replicate your findings. That's all we need. Mean scores, standard deviation, and correlation. That's all we need. And if we have that, those three, We can't run any statistical method. They're all based on the same principle. All right.
Okay. Before we go further, Professor Dogan, I have one question about this structurization model.
Yeah.
Currently, including me, I use PLS.
Yeah, everyone does.
Partial structurization model.
Yeah.
Which software developed from management information systems.
Yes.
Which is not based on theoretical perspective. Rather,
yes, that's true. It's not.
Yeah. Just showing us indirect and direct effect.
Yes, basically, it's a whole bunch of correlations.
Simply little advanced beyond the regression model.
Yeah.
But actually, a structurization model, the benefit of a structurization model is modeling based on theoretical causality.
Yes. No, there is an argument whether it's causality, but it needs to be based on the theory. Because if you do not have fit indices, you don't know if the model is good.
Yes, that's what I'm talking about. The PLS is very simple, available, and easy to use, but they didn't report the fitness of a model. So we don't know that model is suitable or not. But Amos or Lizrel, they exactly target on the fitness of the model first, and then running that model. But these days, the journal, they accepted the PLS in general. Is comparing to the past time. Past time is they didn't accept PLS because of the model fitness.
Yes.
But these days we accept it as it is. What do you think about that, the Amos and PLS application?
No, and when we get papers that are using PLS, we pay special attention to the conceptual part of the paper. There has to be a very strong conceptual discussion, and they have to justify all the relationships.
Okay.
I mean, that's a decision that we make based on the conceptual development of the paper. If there isn't a strong conceptual or theoretical foundation in the paper, then we reject the paper. Usually it's a desk rejection.
Okay.
So for those papers, I mean, with the SEM thing, same thing. We looked at this needs to be based on theory. Otherwise, why are you running this and just run regression? That's the same thing. And PLS, as you said, is basically a little bit more complex regression. SEM is the same thing. It's the regression.
Yeah.
But I mean, Lizrel and plus they report fit indices, but some others they don't report the fit indices, and that raises some serious concerns. I mean, I know some of the editors, they are also being very careful with those types of papers.
Okay.
And there's a marketing war going on between the softwares. PLS works best for many people because they don't need to worry about model fit.
Yes.
But if you are developing, I mean, if you are trying to write a good paper, I don't know, I suggest that you use M+ or something else so that you can see if your model is a good model.
Okay.
I mean, I ask all my students to use M+.
Oh.
I used to ask them to use Lizrel, but Lizrel, they didn't come up with the updates and all those things. Now they are coming up with the updates, but M+ is doing a very good job. Syntax is very easy. I mean, Amos gives some fit indices too. And also PLS, they are trying to develop fit indices for the models.
Okay.
The latest version, they have some type of fit indices.
Okay.
But when you run a SEM type of models, these are the common estimation methods. Okay, I use several of them. We usually use the maximum likelihood. I'll get into that in detail. And then we have, depending on the data, okay, depending on the type of data you have, you can use different ones. They have all different purposes. Some of them requires very large sample sizes, and some of them doesn't require that much. If you look at a maximum likelihood, this is the most commonly used one.
Okay.
When you run SEM on any software, this is the default option. to change the option, then you have to either write in the syntax, or some of them as a drop-down menus. It's the most common. I mean, unless you have a good reason not to use it, just use this. It's easy. And it's makes the estimations based on the maximizing the probability that the observed covariances are drawn from the population. As seem to be the same. I mean, comparing the estimated covariances to your observed covariances. And then I mean, it produces data. It goes through iterations. All the softwares does that. And then this approach doesn't assume uncorrelated error terms, so you can correlate the errors. But when you correlate the errors, you need to make sure that you have a theoretical justification. Can be used for recursive or as far as non-recursive models. It's pretty, I mean, most common one. Then I mean, the assumptions are very simple. It says 100, but it will be really hard to publish a paper with a sample of 100. You should at least get 200 or a little bit more. I mean, if you look at the statistics books, that are recommendation 5 observation, 5 response per variable, or 10. Some suggest too many. So you make your decision, but I mean, if you have less than 200, reviewers will raise concerns about your sample size. And then indicators, variables within assumes that a normal distribution. Your variables have a multivariate normal distribution that are methods to test it. And then you need a value specification of the model. That's another one. And then we usually use continuous variables. If you are using ordinal or non-normal variables, then there are different approaches that estimation methods can use. But if your data is normally distributed, and then if you have continuous variables, this is the best approach. And then I mean, it provides consistent approach to estimation. And then I mean, you can develop this you can use this for a large variety of estimation situations. Scale free. And then if, for example, if you are testing different variation among the scales, this can also be used. And then this method often has lower variance than others. That's a good thing. Okay, they become a minimum variance. Basically, it's unbiased estimator as the sample size decreases. If the sample size is large, then you end up having a problem. So if you have a large sample size, this is not the best estimation method. I mean, recommended sample size for this one is about 200 and between 200 and 400. Okay, and then basically you need to have normal distribution. And then with some of the softwares, you can set the starting values. Most of them, and also in all the softwares, they automatically do it. Okay, they pick a value from your data and then they estimate based on the starting values. But if you know what they are doing, you can ask the software to use a different starting value. And you get different results sometimes. Okay, I mean, for small samples, it's highly biased. For large samples, highly biased. If it's large sample, everything will become significant, like a regression. If you are running a regression, if you have a large sample, very large sample, everything becomes significant because of the sample size.
Okay.
And then we have a generalized least square approach. It's popular when a maximum likelihood is not appropriate, and then it's less stringent. I mean, for example, your data is not normally distributed. Then this is a better approach. And then if you have a large sample, then this is a better approach. Okay, and then we have weighted least square. Again, distribution free, so you don't need to worry about distribution issue. And then if there is a definite violation of multivariate normality, and this might be the choice. Basically, it's again sample size and also what you want to do. There are different approaches, and you don't have to use one or the other one, but you have to justify. And then we have unweighted, again, no assumption of normality. And I mean, sometimes data is not normally distributed. It happens very often. People don't check their data. No. And then they get weird results. And they try to figure out why they are having those problems, because your data is not normally distributed. Check that one first.
Okay.
And there are simple tests for that. Then pick one of these different methods. And then we have ordinary least squares. Sometimes you use that to get initial starting values. And then we go back and use different methods. So we have many different options, depending on the data, depending on the sample size, depending on what you are trying to do. I mean, when we do SEM, this is what we start with. First, we assess the model fit. Okay. First, we assess the model fit. Basically, we examine goodness of fit indices. And there are many different ones, and you can calculate every single one of these by hand. Okay, there is a formula for these calculations. And if you are using, for example, PLS, you can also calculate these by hand. But the problem is many people don't know how to calculate them. If you Google it, there's a thing called Google, and then it will give you the formula. And you can calculate these by hand. Usually, and when I teach the SEM class, I make my students calculate stuff by hand. The software provider, huh?
Really?
Yeah, this is very easy. It's not very complicated calculations.
Okay.
And the software gives you the result, but you need to understand how they are calculated.
Okay.
If you really want to know, you need to know the calculation. And the software will give you the result. There is no question about it. And then depending on the software you sometimes you get different results. You test the same model using different software, we get different results.
That's right.
Not that different, but slightly, but still. And then you need to look at the estimations. You need to examine the statistical significance of individual parameter estimates, and then magnitude and direction. Sometimes people get a weird direction. They say this is going to be a positive relation. They end up getting a negative relationship, and they cannot explain it. And then you need to evaluate construct validity. And then, you need to look at the model strain, whether there's an ill fit. The model doesn't work. If the model doesn't work, there's no point using this approach, honestly. Use regression. You will get the same results. Simple. Then you don't have to do a whole bunch of explanation. And if you need more information on these things, Klein has a book. If you read the chapter 8, and then Schumacher and Lomax's book, chapter 5, it will give you more information on these issues. And then goodness of fit. I think we all know what this is. Indicates how well the specified model reproduces the covariance matrix among the indicator variables. Right? Usually, for this one, the initial measure is always the chi-square statistics. I think everyone knows chi-square. You studied when you are taking your undergraduate degree. That's the lowest level of the statistical knowledge. And the null hypothesis is that there is no difference between two covariance matrices. Since you don't want the matrices to be different, you hope for insignificant chi-square. You don't want chi-square to be significant. But with complex models, that rarely happens. If you have a complex model, okay, usually you end up with a significant chi-square, because it's very sensitive to sample size. It's very sensitive to the number of estimations. So we use chi-square as the initial starting point. But if we do usual model comparisons, we compare the models based on the changes in the chi-square. So because of the chi-square issue, because of the sample size issue, people also use a norm chi-square, basically chi-square divided by degrees of freedom. We will talk about what's acceptable. And then we have goodness of fit indices, GFI, CFI, and there are a whole bunch of them. And also we have badness of fit indices. RMSEA, RMSR, they measure the badness. If they are high, then you have a problem. With the goodness of fit indices, you want them to be high. With the badness, you want them to be low. So there are two distinctions. And different people use different criteria. We will talk about those criteria. I mean, and also depending on the model and a sample size, if you have a small sample size, you may want to use a very strict criteria. Because in small sample sizes, results are usually inflated. Okay, they are inflated results, so you want to use more strict criteria. And then more complex models with larger samples, I mean, you don't use the same strict criteria. All right, we have 3 different types of fit indices.
Okay, Professor Dogan, probably some of the students here have experience of a structure equation model.
Okay.
About chi-square, about the model fitness. If you have any question about this, this part, you may ask to Professor.
Yeah, if you have any question, just ask the question. I mean, don't wait until I finish.
Okay.
I'm just showing you what you guys supposed to report and what type of fit indices. And then, I mean, we do the absolute fit indices. Basically indicate how well your estimated model reproduces observed data. Then we have incremental for model comparisons. It compares the model to a baseline model, and then we have parsimony. And people don't pay much attention to parsimony fit measures, but those are very important because you want a parsimonious model. You can put a whole bunch of variables into a model or a regression equation, and then you can explain, I don't know, some variance. Well, you want your goal should be to identify the variables construct that explains the most. That's why, I mean, we need to pay attention to parsimony fit measures. And then guidelines, use multiple. Don't report the ones that works. That's usually what people do. Then you get a paper, you look at the fit indices they report. You can easily guess which one didn't report because it didn't work, because they never report those. Okay, and then adjust the index cutoff values based on model characteristics. Remember, for simple models, very strict. For a more complex model, you can use a less strict criteria. And remove indicator variables that do not meet established criteria. Sometimes it doesn't. Sometimes we remove the whole construct because it doesn't work with the model. There are issues, but I mean, then you come up because your goal is to develop a good model with a SEM structural equation modeling. That's why the name suggests structural equation modeling. Doesn't say structural equation testing. The name has modeling in it. So the goal is to have a good, reliable model. And then we use goodness of fit indices to compare models. You know, if we go back, we have incremental fit measures. They compare models. And then, I mean, the goal is to come up with a good model. Okay, you want to come up with a true model. So you don't want to come up with a better fit. You want to come up with a better field, and also you want to come up with a model that you can explain by a theory. Those are the two requirements. You should be able to explain your model by theory. If you cannot do it, then run regression. There's no point using a modeling approach. If you are looking for the relationship between two things or three things or four things. SEM is modeling approach.
Okay,
Yeah,
here, question.
Sure.
Like when you said, the SEM is modeling. The modeling should be fascinating, should be interesting to the reviewers and editors.
Yeah, of course.
We bunch of theory, combine the overarching theories, and then take variables out of that overarching theories. Sometimes that, their motivation actually make trouble, like a modeling fit doesn't work very well.
Yeah.
There must be a trade-off between theory and the actual modeling fit.
No, there is not. Basically, if your model fit is not good, that means the theory you use is not a correct one, or
Okay.
you do a good job with your research.
Okay.
And we cannot blame the model fit for the bad model.
Okay.
Because people make lots of mistakes. I mean, as I mentioned before, they don't check the distribution.
Okay.
Maybe you need to use a different estimation method.
Okay.
If your distribution is not normal, or there might be some other issues. But
so you mean it's a modeling fit is not a problem of the theory. It's a problem of the data distribution.
No, it might be theory too. Maybe you
Yeah.
theory says something, but you don't apply it correctly.
Okay.
It's also application issue.
Okay.
And sometimes people, I don't know,
Mhm.
they try to surpass. But if there is an established theory,
Mhm.
and if you are using the established theory,
Mhm.
your model should be, should work out fine. If usually, in most cases, in those cases, it is your data.
Okay.
You don't get the data from the right people. There's a problem with data collection. There are lots of missing values, and there is something going on.
Okay.
Because if 100 people test the same thing,
Mhm.
they get good results, and you don't get good results.
Okay.
What might be the reason? Or
None of
let's say 90 people tested, 100 people test, 90 people got good results, results that make sense. And then some people don't get the results that make sense. Especially for established models, established theories. And people sometimes use, they try to fit the theory to the data they have.
Mhm.
So they have the data, and then they try to come up with a theory to explain the data. It's not the right way of doing research. You're supposed to start with the theory. I mean, there are lots of people that are doing it. It's very common these days.
Yeah.
And that's creating issues.
That's right.
That's why these stuff, especially the model fit issues, I think they are very important, even though not many people care about these days. But if you are doing model development, and I mean, if you want to, what I found is most established people in the field, okay, they establish themselves because they do research on a theoretical conceptual model development. If you, unless you do research on some hot information technology topics, you get lots of citation. But beyond that, if you look at most people, it's about the model development. For me, I get most of my citations from papers that did a model development. We published one paper in, I think, what journal is it? International Journal of Information Management. And we are getting lots of citation because we developed a model for artificial intelligence device use. You get, amazing how much citation we get from that paper. And we just let it be published in 2019. For that type of paper, I think it's getting a very good citation. And it's one of the highest cited papers in the journal. And people keep citing because of the model. I mean, there was no model. I think there are a few models now. Still, people are citing it. So, global fit index, chi-square, the first one. Okay, and if you have a large sample, then it will be significant. It will be significant. But the thing is, with all the fit indices, they are all based on the chi-square value. They all use the chi-square value and also degrees of freedom. That's why, I mean, this is a good baseline. We have a goodness of fit index based on the ratio of the sum of square difference between the observed and produced matrices to the observed variance. This is absolute fit index, and it's 0 to 1, depending on who you ask, 90 or 95, depending on the model. If you have a simple model, 95. If you have a complex model, 0.9 works. And then we have JFI. This usually gives a higher values than other coefficients. Again, it's affected by sample size. You need a sample more than 200. If you have a smaller sample, your JFI won't be good. Then we have adjusted, basically adjusted for the degrees of freedom, depending on the complexity of the model. This is more applicable for complex models. Again, depending on the model. I mean, then we have a root mean square residual. It's an absolute fit index. Basically, this is one of the badness of fit index. Okay, and then this is basically error variances. You want a value less than 0.06 or 0.08. Again, depending on the complexity of the model. Simple model, 0.06. Complex model, 0.08. Less than 0.08 is acceptable. Then we have, again, standardized root mean square. This is another absolute fit. And then, I mean, this is the mean discrepancy between correlations observed in data metrics and the correlations predicted by the model. Again, this is the badness of fit index. For simple models, 0.06, less than 0.06, or more complex models, less than 0.08. Then we have, I mean, another one. Again, this is also a badness of fit index. Then these are the acceptable variances. 0.05 close fit, anything between 0.05 and 0.08 acceptable. If it gets higher than 0.08, that's usually marginal fit. Yeah, you get close to the 1, poor fit. And I mean, people pay attention to these things. Because if these numbers, especially badness of fit index numbers, are high, that indicates problems with your data. And then these are very good tools to identify if you have a problem. Maybe maybe there are outliers in your data. You need to get rid of those outliers. You need to run some outlier tests. They're usually caused by the outlier most of the time. So I mean, before running any statistical approach, do the simple stuff. Look for the normality, look at the distribution, and there are very simple tests. It doesn't even take that long. And then try to identify the outliers, get rid of the outliers. Because if you have outliers, you will never get the results you hope to get. They'll mess it up. You can easily identify them, and there are lots of tests for that. And then we have the incremental fit indices. Basically, this one compares your model to the baseline models. Okay, most of the softwares will give you the results for these types of fit indices too. Then we have the norm fit index. Again, this is it's a measure basically to rescales chi-square into 0, and then if it's 0, it's no fit. 1 is perfect fit range, similar to all the other ones. And then it compares a restricted model with a full model using a baseline null model. So it's basically comparing a different model. Again, 0.9 or 0.95 is acceptable depending on the complexity of the model. If your sample size is small, then it's not a good fit index. Then we have non-normed. It's a comparative fit index. Sometimes you get the results higher than 1. And when usually people get a result higher than 1, they don't report them. But I mean, that this one compensates for a model complexity. It's good for complex models. Yeah, very complex model. You may want to pay special attention to this one. And then we have the comparative fit index. Measure the relative fit. Comparison of your model to a baseline model. Again, 0 to 1. The minimum value, 0.9 or 9.95. Again, complexity of the model. And then we have incremental fit index. There's another one. Sometimes they use different names in different softwares, but very similar fit indices. Again, I mean, you want something higher than a 0.9 or 0.95. And then this one addresses the issue of parsimony and sample size. Okay, parsimony and sample size. Again, the complexity of the model and the sample size. And then model parsimony. This is very important because with the modeling, that is what we are trying to do. We are trying to come up with a parsimonious model. That is the main goal of this modeling stuff. You don't want to find, you want to identify the most important constructs, most important variables. And this one, these indices tells us which model is more parsimonious than the other one. Again, this is a parsimony model norm fit index. It's a modification of the NFI. And this one takes into account the number of degrees of freedom used to obtain given level of fit. And the other one is a modification of GFI. It does the same thing. Again, if you remember the earlier discussion, GFI is better for some models and NFI is better for some other models. Depending on the type of model you have, depending on the complexity of the model, depending on your sample size, you use one of these. And if you know what you are doing, it's very easy to justify why you only report this. And there are lots of research behind these things, and you have the citations. It makes your life easier if you are submitting a paper to a journal. Some editors, I personally look for these things. People are randomly reporting some fit indices. I know that there's something wrong with their data. So you need to provide some kind of justification. Again, thinking about the fit indices, norm close to 1. I mean, not affected by sample size, GFI, NFI. There's a penalty action for extra parameters. Parsimony fit index. You want to come up with the parsimonies. And then consistent across estimation techniques. I mean, these fit measures, these are desirable properties of the fit measures. But you need to report the right one. That's very important. Not the ones that work out for your model.
Okay, here.
Sure, go ahead.
You introduced very important knowledge to our students. The students are probably some familiar with structural equation modeling. They may understand what these indices stand for.
Yeah.
Anyway, but here are several indexes we can apply for. But what is the best and most important indexes for making the acceptable research model? We have a GFI, HFI, and NFI, CFI, RNF, and sort of things, but we cannot make them satisfied overall.
No, so, basically, it depends on the model complexity.
Okay.
Okay, depends on the number of variables you have, depends on the sample size.
Mm-hmm.
For different things, you can report different fit indices. Mm-hmm. For complex models, I mean, usually everyone wants you to report chi-square and degrees of freedom. Mm. And then goodness of, I mean, if we go back GFI, usually you should report GFI, But with the, I mean, if your sample size is small, you are going to have a problem with this. So you need a decent sample size. Okay, you need a sample 200 or more with this one. But as we discussed before, if you are using a sample size of 100, I mean, that's acceptable to run the model, but GFI is not going to be the best. But usually we report the chi-square and GFI, and then adjusted GFI, depending on the complexity of the model. A very complex model, then this makes more sense sometimes. I mean, you report these, and then you can report this one, okay? And then you need to report some goodness of fit and some badness of fit indices. We need to know what's going on with your error variances. And then you can report, depending on the model, you can report some of the incremental fit indices, depending on what you are trying to establish, what you are trying to do. And then some of the comparative fit index indices. You don't have to report all of them. But you need to tell us why you're reporting that one. Might be the context of the model, it might be the number of variables and sample size. You may have distribution issues. When you're writing these things, I mean, if you do a good job and if you're honest, most of the time you can justify this stuff. This is the answer to your question. I think we discussed this. Yeah, this is the answer to your question.
Actually, honestly, when I writing papers, I pick the most important indices as threes, GFI and HFI.
When people write papers, they report the ones that works.
Yeah.
This is what you need to report. Okay, you have to report the chi-square.
I report, but you know, sometimes I cannot make them satisfied. So I highlight GFI, HFI, CFI.
Yeah.
To proceed reviews. Is my model is acceptable because it's beyond GFI, NFI, and CFI.
Yeah.
But some of the RMF and the RMSEA is not. Is borderline.
You have to report them because
yeah. It's reported, but I slightly. Yeah, it's a report, but you know, sometimes they say, "Oh, this is not the acceptable, you know, number and criteria."
If it's not acceptable, then you have a bad model.
Yeah.
That's the problem. And if the one number is acceptable, you have a bad model, so you have to make some changes.
Okay, right.
You need to fix them. Because I mean, there are everyone uses a different. I mean, there are established standards, but some people want more restrictive numbers.
Okay.
But you must report CFI degrees of freedom and significance. I mean, chi-square degrees of freedom and significance.
Yes.
And then standardized RMR and RMSEA, because they are very important because it tells us what's going on with your data. If they are higher than 0.8, there is a problem with your data. You need to figure it out. Again, as I mentioned before, it might be distribution. There might be maybe not normal distribution. There might be outliers. Or sometimes, you know, when we enter data, we're supposed to enter 5, but we enter 55. And that messes up the whole data. And these numbers will tell you if there's a problem with the data. That's why you have to report them. And then additional fit indices, you can report GFI, NFI, or CFI. Okay, NNFI or AGFI. And then PNFI, PGFI, or AIC. Not many people report AIC. Basically, overall, more than one model fit should be reported. But you have to report chi-square, degrees of freedom, and significance. Nowadays, we get many papers, people don't report degrees of freedom. They just report the norm chi-square divided by degrees of freedom. And we send some papers back because we want to see degrees of freedom, because degrees of freedom is very important. Because especially if you are trying to see if people are telling the truth, the first thing I do is I look at the degrees of freedom in their measurement model, and then degrees of freedom in their structural model. And then you can tell if they made some changes, correlated some of the errors. There are some other correlations in the model that are not reported, because measurement model is supposed to have the highest degrees of freedom, yes? And if your structural model's degrees of freedom is different, if there are significant differences, because you can see how many hypotheses you have. You have 10 hypotheses, basically your measurement model, and you can easily estimate if they are telling the truth. And we have papers that are differences, 100 difference in degrees of freedom between measurement model and structural model. There is something going on in those models. So basically, this is what you need to report when it comes to fit indices. And these are some of the basic overall summary. Fit indices, acceptable threshold. Low chi-square, relative degrees of freedom. And depending on who you ask, some people says 2 to 1, 3 to 1. Different people use different criteria. Again, root mean RMSEA. Some people said 0.6, 0.07, 0.06, or 0.08. Some people even push for 0.04. Everyone has different criteria. JFI, again, 0.95, 0.95 for restrictive, very simple models. And then RMR less than 0.08. Then we have NFI, NNFI. I think some models call it a TLI. And CFI recommended is, depending on who you ask, 0.9 or 0.95. Then these are the global fits. These are you're supposed to report. And then you look at the parameters, whether they are significant. And for that one, we look at t-values, t-scores. And also we need to look at whether they are substantial. Sometimes you find a significant result, significant effect, but the effect is so small it doesn't make sense. So you need to make sure that they are significant. And then another criteria you need to use is, do the relationships make sense? And remember, this is model development. So relationships needs to make sense. Sometimes people come up with a model, and then later they come up with a modified model with a whole bunch of new relationships. If you cannot test the model you develop based on theory, then there is something wrong. Okay. And then does a particular part of the model fit or not fit? Sometimes, everything works, but some part of the model doesn't work. And most of the time, some of the reason for that one is the culture. People adopt stuff that was developed for Western cultures, and they try to use them in the Eastern culture, and they get different results, and or some part of the model may not work. So you need to pay attention to which part works, which part doesn't work. Next, so you make sure that you have good fit. You have a good model. Okay, next, what we do is we go to, and we said we go through two-step process. First, measurement model, and then we test the structural model. And then when we assess the measurement model, we look at several different things. First, a construct validity. And there are a whole bunch of, I'm sure everyone knows what they are. And then we look at assessing the structural fit. Okay, first step. Test the confirmatory model. It's basically regression, and it specifies the positive relations of the observed variables to the underlying constructs. And second step, you test the structural model. Make sure that first you make sure that your constructs are okay. Okay. And there are lots of different tests to measure these things. Lots of different tests. I'll go briefly on some of the ones that we use, and that one that makes sense. And I also show some of the calculations, because I mean, you need to understand how these things are calculated. And this is a simple, very simple model. This is a model we published years ago. I think we published in Journal of Travel Research. This is a model. Very simple. This is the covariance matrix. And everyone knows what a covariance matrix is, yes? Do you guys know the difference between regression and then a covariance? In regression, you don't have the standard deviations. Covariance matrix, standard deviations are integrated. If you want to calculate, if you want to come up with a covariance matrix, you need to have the mean scores, and then correlations, and then if you add standard deviation, then there are software that will calculate the covariances. All right, the measurement model specifies the pattern by which each measure loads onto a particular factor loadings. Okay, another mistake people make when they run a regression. Okay, they have one data set. They use that data set for exploratory factor analysis, and then they use the same data set for confirmatory factor analysis. That is not acceptable. You're supposed to use two different data sets if you are using exploratory and then confirmatory factor analysis. You cannot use the same data set for exploratory factor analysis and confirmatory factor analysis. Because if you use the same data set, what you are doing is you are figuring out something, and then using the same data, you are confirming it. And you will confirm it, because it's the same data. That's why you need a different data set. A measurement instrument needs to be fully developed and a factor structure validated. If you are going to use something for a measurement model, it needs to be fully developed, and then it needs to be established or validated. That's why we go through if in a scale development process, we go through exploratory factor analysis and then confirmatory factor analysis, and we use different data sets. The stuff you use in confirmatory factor analysis, okay, this is not the place where you develop the measures. You use established, validated measures. You know the factor structure. You know the factor structure. You are just making sure that there is nothing wrong with the data or something, and then that's why it's called confirmatory factor analysis. If you want to identify the underlying dimensions, use exploratory factor analysis. Basically, when you are testing for the validity of the factorial structure for an assessment measure, the researcher seeks to determine the extent to which items designed to measure a particular factor actually do so. So we know what items supposed to go into measuring a construct. We just confirm it. That's the whole purpose of a measurement model. Just confirming it. If you are developing something, use exploratory factor analysis. And that's very important. And you need to use different data set. Basically, confirmatory factor analysis and construct validity. One of the biggest advantages of a CFA, they call it confirmatory factor analysis measurement model. I mean, you can assess the construct validity of the proposed measurement theory. And the definition of the construct validity is the extent to which a set of measured items actually reflect the theoretical latent construct they are designed to measure. So they are validated, they are established. There is no question about them. Sometimes, I mean, we have problems because of the cross-cultural issues. But if that's the case, you may want to do a scale development study first. And there's a different process for that one. Before running a CFA model, and this is important, phase validity. Phase validity. You need to assess the validity based on the phase. Do you guys know what phase validity is? You look at the items and then ask people, experts, to see if it makes sense to use those items to measure a certain construct. If it makes sense. You just talk to a few people, and then, I mean, whenever we do, for example, studies, we usually do pilot tests. And we ask people to see if it makes sense. And then we look at published results from previous studies to confirm that we are using the right items to measure a scale or a construct. And then you do pre-test or a pilot study. And you're supposed to do these things. Sometimes you report them in the paper, sometimes you don't report them, but usually we do these things. And usually when I do these things, I do on students. I'm not looking for the relationships. I am trying to figure out if the items I am using are measured in the construct. So student sample works fine with these things. I mean, the major objective is to estimate the validity using more rigorous approaches. And we will talk about it in a minute, and then we will see how to calculate those things. Okay, when you have a measurement model, or when you have a construct, each construct should be measured with multiple observed indicators. Minimum recommended is 3 or 4. Okay, 3 or 4. And then measured, basically, those are the observed indicators that are posited as alternate indicators of each construct must be acceptably unidimensional. So you have to do a unidimensionality test. You need to make sure that the items you are using to measure one construct doesn't load onto other constructs. That creates problem. Do you know what people do if that's the case? They correlate the errors to minimize that, and then it messes up the model further. You get good fit indices, but if the reviewers or editors realizes what you did, they just reject your paper. And it happens very often. Each indicator should measure load only on one construct. That's what unidimensionality means for each construct. Before testing the overall measurement model, usually people put a whole bunch of things and they test the whole model. My suggestion is test them one by one to make sure that they are unidimensional. Because if you are testing a complex measurement model, sometimes it's really hard to identify and figure out what's going on if you don't get good results. But if you test them one by one, I mean, if a construct has 4 indicators, then you can test it as one construct. But if the construct has 3 indicators, then you test 2 constructs at the same time. And it will give you the chi-squares and goodness of fit indices. It makes life easier. Rather than what people do is they have no idea what's going on, so they end up correlating a whole bunch of stuff that are not supposed to be correlated. Sometimes you start with a larger number of variables and you eliminate some of them. As long as you have 3 or 4 measuring each construct and they make sense, then that's okay. You guys, any question on this? This makes life easier. You want to make your life easy. You don't want to spend 3 months analyzing your data. That's why it's start with small pieces, not the whole thing. Makes it easier. Basically, constructs with unacceptable fits, if you are doing 1 by 1 or 2 by 2, then you specify them. You delete some of the items. Makes it easier. And then let's look at this model. It's a simple model. We have a 4 item measuring 1 construct, and then we have or item measuring another construct. The chi-square, and it looks okay, degrees of freedom is 2, and then p-values are very high. So RMSO scores are RMSEA scores are very low. So it looks like these are reliable, and they are reliable because they have been used in the field over and over, over and over, over and over. These are valid measures. And if your results, if you end up getting something different than this, then you need to go back and look into your data. Seriously. It happens sometime. I mean, sometimes we ask students to collect data, help us with data collection. Do you know what some students do? They take them home and they fill out the surveys themselves. Yeah, it happens.
Yes,
We
sir.
have to get that issue sometimes. That's why I mean, we usually these days don't ask students to help us with data collection unless we have a trained assistants. That's the issue. That was an issue, and that's still an issue, especially if you are sending people out to collect get data from different groups. When we do tourism impact studies, that's usually what we do. We used to do. Now we are using companies. And then this is basically what your measurement model looks like, okay? If you look at the measurement model, I mean, all these, all the constructs are correlated. Okay, all the constructs are correlated. And then you have the error variances, that 0.32 is the error variance. And then a 0.82 is loading. And then we have the correlations of all the constructs are correlated. And for this one, chi-square is 85.73 and degrees of freedom is 51. So if I am running a structural model, okay, if I am running a structural model, in the structural model, chi-square value should be, degrees of freedom should be higher or lower than 8.51. Should be higher or lower than 51. Degrees of freedom in a model, structural model, should be 51 or higher. Okay? If it's lower than 51, that means authors did something that they are not supposed to do in the structural model. I mean, sometimes it's okay to correlate the error variances, but you have to let people know and then explain why you did that. If it's less than 51 degrees of freedom, that means you correlated some of the error variances. Okay? And if you didn't mention that, that's a really good reason for dash rejection. You are doing something that you are not supposed to do. I mean, you can do it, but as long as you tell us why you did it, then it makes theoretical sense. Do you guys understand that? That's why I want to see degrees of freedom when people submit the papers. But that's the criteria that I use to see if they did stuff that they are not supposed to do and they are not reporting it, or if they did things that they are not reporting to improve the model fit. And unfortunately, people do that. I mean, if you look at this one, the goodness of statistics, there are a whole bunch of those. This is from Lizzo. I think MPlus produces something similar. This one, relative chi-square. That's basically chi-square divided by degrees of freedom. I mean, you report chi-square, degrees of freedom, and also you report that one. A value below 2 is preferred. But these days, most people use the below 3 criteria. And then we have the chi-square. That's a likelihood ratio of chi-square. There is another one. And then we have the CFI. And this one is a 0.991. It exceeds 0.95. This is a simple model, so we need to use a 0.95. And then we have a AGFI, 0.948 is, I mean, for a simple model, it's borderline. But I mean, we can use the sell this using a 0.9 for the model that we just run. And then a GFI is 0.96. So that's acceptable. And if you look at most of the fit indices, they are acceptable. And then we have three types of models. We have default, saturated, and independence model. Default model is your model, your theoretical model. The saturated, everything is correlated. Everything is correlated with each other. It's like a measurement model. And then independence model, nothing is correlated. So it's comparing your model to those two models. Yeah, when we evaluate the measures, we use the numbers for the default model. Okay, that's your model. And then RMSE represents the degree to which lack of fit. It's either due to misspecification of the model tested versus being due to sampling error. You see, it's a sampling error. Either it's a misspecification or the sampling issue. That's why we need to see these badness of fit indices. And then a RMSEA is an absolute fit index, and in this case it's 0.041. I mean, it's quite low. I guess this is acceptable. And then if you look at the 90% confidence interval for the RMSE between low and a high, it's not even it's lower than 0.08. So these are acceptable numbers. And then GFI, we talk about this. It's an absolute fit index, 0.96 is acceptable. CFI, incremental fit index, is also acceptable. And CFI represents the improvement of the fit of specified model over a baseline model, whether everything is constrained and uncorrelated. Then we have a PGFI, a parsimony fit index. Lower value is better because you want a parsimonious model. And then we have a Q-plot distribution. Basically, it shows how your data is distributed. You can get this using SPSS. If you look at the distributions. And then we look at those. And also look at all the residuals. I mean, if you look at the residuals, scores weren't that bad. They were within acceptable range for our sample data. If you look at here, it's like distribution. I'm sure you guys have seen this, something like this. You can generate this with Lizral, or you can generate this with M+ or SPSS. When you look at the distribution, you want a straight line. And this looks somewhat okay, that we don't have any major distribution problem here. Well, if it was all over the board, then you may have a distribution problem. And when you do skewness on curtices, and then when you look at this SPSS does those, it also gives you the same information. And this is important to do it before you run the data. Identify your outliers and also make sure your distribution is okay. If you come up with a non-normal distribution, and usually when you get rid of the outliers, sometimes it solves the problem. And the model fit, basically using chi-square, GFI, CFI, and RMSE. Basically, I mean, all the fit indices are good. So it looks like the model looks good. That's the first thing we do. We look at the model first before we look at anything else. If the model is not good, there is no point moving forward. So you need to have a good model, then you move forward to the other items, other issues. Then we look at the construct validity. So we talk about the phase validity. I mean, the extent to which The content of the items is consistent with the construct definition. Basically, it's a judgment thing. Then we have conversion values. I think everyone knows what this is. The extent to which indicators of a specific construct converge or share high proportion of variance in common. We measure this with AVE, average variance extracted. Then we have discriminant validity. Okay, these are basically the constructs are different. Then we have nomological validity. That's basically you look at the model and then the results are as predicted. Okay, and then we look at the reliability. That's basically internal consistency of the observed indicators. I mean, we do all those things in a paper and report all these. Conversion validity, there are three measures. When you look at the conversion validity, the factor loadings. That's the one thing we look at, the factor loadings. What is an acceptable factor loading? Again, depends on who you ask. Different people use different criteria. It might be 0.4 or 0.6. And then we look at average variance extracted scores, and then we look at reliability. Standardized loading estimates should be 0.5 or higher, ideally 0.7 or higher. It's really hard to get. Your AV scores should be 0.5 or greater. That means, I mean, if AV score is 0.5, that means at least you are able to explain 50% of the variance. If we cannot even explain 50% of the variance in that construct, then what's the point of having that construct? And then AV estimates should be greater than the square root of the correlation between the factors and the other factors to provide evidence of discriminant validity. Reliability should be 0.7 or higher. And these are some established criteria. But this is how we do it. I mean, this is from Lizrel. And then we have the calculations. The first number, second number, and the third number. Third number is basically the t-test. If it's higher than 0.96, then they are all significant. These are unstandardized loadings. And then we have the first line represents unstandard estimate. There's a parentheses. That's the standard error. Okay. And then third line represents t-value. And a t-value on 0.96, that's usually that means it's significant at a 0.05 level. Most often that's the level that we use. And then these are the completely standardized solutions. And then we use usually completely standardized solutions results for the testing or conversion and a discriminant validity. Again, standardized factor loadings. And then the first thing we'll look into, this is the first thing we'll look at. You don't want very low factor loadings. Should be, I mean, depending on the criteria you use, sometimes we use 0.4 too. 0.5 or a 0.7. And then all loadings need to be significant. If you go back to the previous one, unstandardized results, all the loadings are significant. And then, I mean, it looks like they are okay. Some numbers we have a 0.592, but the rest of them are either very close to the 0.7 or higher than 0.7. So this is the first criteria. Then next, when examining conversion validity, we look at two additional measures, AV score and construct reliabilities. I mean, some softwares calculate these. Sometimes you have to calculate by hand. That's basically what it looks like. You see that the first column, those are the factor loadings, standard factor loadings. And then you have item reliabilities. And then you have the error variance. The easiest way of estimating, calculating item reliabilities is either you can get the square of it, or 1 minus error variance will give you the item reliability. And then when you add the standard loading, you can easily calculate estimated variance. And then we will see how to do the construct reliability. When you look at these, all the AV scores are higher, and then construct reliabilities are higher than the threshold values. This is how we calculate these. These are the factor loadings, square factor loadings. Another way of finding it is 1 minus error variance will give you the same number. Error variances. Again, if you want to find the error variance, you can 1 minus squared factor loading will give you the error variance. And this is like the eigenvalue in a factor analysis. You add those up, and that will give you that number. Item reliabilities, and then if you divide it by the number of factors, it will give you the AV scores. Then, I mean, if you look at the variance extracted, I don't know how well you remember your stat classes. Okay, the sum of square loadings, basically that's what this is. And sum of square loading is this thing. Sum of square loadings. Oops. Oh, can you guys see? Yeah, here. These are the square loadings. These are the square loadings, and that's the number, sum of square loading here. Okay, and then we have the constructs. These are the square loadings. Add them up. You get for the first one 2.264 divided by 4. It gives the AV score. Very simple calculation. So if your AVs, if you have a problem with the AV score, so you can figure out why you have a problem if you know how to calculate this thing. And then this is the square loading. And then I mean, if you look at the formula, it's a very simple formula. It's not very complicated. And good rule is 0.5 or higher for AV. And there are different. Nowadays, what happens is people come up with different measures because their AV scores sometimes they are not good enough. They cannot justify the discriminant value, so they are using different scores. But this is basically, I look at this when I try to figure out if a measure is a good measure. I don't care about the other items. And then we have the construct reliability. I think this is also a very simple calculation. The sum of the loading squared. We saw that one. And then we have, this is how we calculate it. Basically, the loadings squared divided by loading, sum of loading squared plus error variances, and then it will give you the construct reliability or composite reliability. Again, these are simple calculations. And softwares, some softwares provide this information. And again, if you know what goes into it, then if you have a problem, you can figure out why you have a problem. When I look at these calculations, I can usually figure, if you know how to calculate it, you can easily figure out where the problem is. If you have a low composite reliability. And this is sum of the square loading squared, and then this is sum of the error variances. And again, a construct reliability, the good score is 0.7. But if you don't have 0.7, you can also justify 0.6. I mean, we did some papers, we couldn't get 0.7. There are references that you can use to justify 0.6. 0.6 or higher. And then, I mean, conversion validity, basically taken together, I mean, looks like we have the conversion validity, yes. Our loading estimates are 0.7, just two of them were lower than 0.7. And they don't harm the model. And average variance extracted plus 0.5, or construct reliabilities were above 0.7. This is the stuff that you need to report. when you are justifying your measurement model. Then you go and you look at the discriminant validity. And that's also a simple process. The extent to which a construct is truly distinct from other construct. And there's a rule of thumb. We already talked about this one. All construct average variance extracted estimates should be larger than the correspondence squared interconstruct correlation estimates. And then if they are, then your measures are okay. And this is how we do this one. I mean, this is what we found. These are the correlations point. These are the correlation scores. Now we need to find out if they are correlation between different variables. And then this is how we calculate discriminant validity. In the columns below, we calculate SIC squared interconstruct correlation from the interconstruct correlations obtained from the correlation table in the output. I mean, this is from a list, from the list output. And these are the interconstruct correlations. And then we have the AV scores. Compares the average variance extract estimate for each factor with the squared interconstruct correlation. So we get the square of that one. Then we look at it. So which one your AV score should be higher than your interconstruct correlation? Yes. And then all variance AV estimates in the above table are larger than the corresponding square interconstruct correlation estimates. So we have the discriminant validity, basically. And there are different ways of reporting it in terms of the table. And this is one simple way of doing it. If you have a larger sample, you just come up with the correlations, and then you put AV scores in as the diagonal value. And then you report the squared correlations. So you can look at, you need to make sure your AV scores are higher than squared interconstruct correlations. And the interesting thing is, I mean, I have seen so many papers submitted. People say they have discriminant validity, they report these things because software generates them, but they don't know what it is. And then you look at the table, there's no discriminant validity. People don't even realize it. That's why you need to know what these things are and how to calculate these simple stuff. These are very simple stuff, not that complicated. I mean, running a SEM is not that complicated. It's very easy, very simple process if you know what you are doing. If you don't, then it makes it a very, very complex. And then you look at this one, nomological validity. Tested by examining whether the correlations between the constructs and the measurement model make sense. If they don't make sense, there is no point going and testing the structural model. So they need to make sense. I mean, the constructs in our theory suggest that they need to be positively related based on our theory. If the relationships are negative, then there's something wrong. And then we look at this one square. If you look at here, these are the correlations among the variables. You see all positive. Look at these correlations, and then we know that our model is okay. And then you look at, apparently, for some reason, this didn't show up. T-scores, this is basically the same thing, but with the T-scores, I was a table, apparent table disappeared. And then we look at square multiple correlations for the variables. And then a square multiple correlation for the others, so it looks like there are no problems here. These are the R-square values. So if you subtract these from a 1, you will get the standardized error terms. I mean, we saw them earlier. And then the squared multiple correlation are also referred as the squared loadings. These are the square of loadings. And then square loadings are used in calculating the average values variance extracted. So, I mean, if you have a problem, what do? In addition to evaluating goodness of fit statistics, you also need to look at these things, path estimates. Your loadings that link the individual indicators to particular construct from 0.7 or 0.5. 0.5 is acceptable, sometimes 0.4 is acceptable too. Variables within significant or low loading should be considered for deletion. If the loading is not significant, don't include that in your model. And then you look at the standardized residuals, the individual difference between observed covariance terms and the fitted covariance terms. The better the fit, the smaller the residual. So anything less than 4, they are candidate for deletion. And then we have the modification indices. All the softwares provide that one, so you look at those, and then you eliminate them one by. If you are making changes to a measurement model, you delete items one by one. You don't delete 5 items at the same time. It's a process, one by one process. Because sometimes you delete one item and it solves the problem because that the error variance of that term, that item might be correlated with others, and that may solve your whole problem. But if you delete 5 of them, then you will never know that. Okay, I mean, this is a modification indices, and you look at this one, and then you usually look at with the largest one, whether positive or negative. This one over here is 2.882. So you look at those, and then to see if you need to delete that one. But if you are deleting something, make sure that you end up with enough items to measure a construct. You need to have at least 3 items for each construct. The largest 2.882. So I mean, no residuals in this model exceeds 4.0. So we don't have the problem. So we don't need to delete anything in this example.
Okay, Professor Dogan.
Yeah.
We are running out of time, so
okay, it's almost done. I'm almost done.
Okay,
I thought this
I
was
want
going to be
give
9
this question to students. Students
All right.
may have their question for your
Okay,
presentation.
Sure. Okay, if the measurement model valid, then if it's okay, then you don't need to do anything. If it's not, then you need to design a new study. Okay, and then you do the structure of the model. Again, you do the goodness of fit index and all the other stuff. And then based on that, you decide if you look at the effect sizes, significance, direction, and the size. And then you make a decision based on those to whether the model supports your hypotheses or not. And this is the model we tested. And then if you look at here, 3 constructs, we have both exogenous and endogenous variables. And these are the results, and everything looks significant. All loadings are significant. And if you look at the t-scores, they are all significant. So all the items are significant. So the paths are significant. Again, coefficients are significant, and these are the t-test scores. And then standardized results are significant. And then estimated square correlations, it extends on the 0.28, not very large. All right. Now I think I can take the question. I thought I had time till 9 o'clock. That's what the schedule said. No, my 9 o'clock. I think you're 12 or 8.
Okay, very nice presentation from beginning to the end about structure equation modeling. Wow, this is a very critical method for making papers. Anyway, we have 20 minutes. Students, if you have questions, it's a very good chance to ask him, the expert of SCM.
I'm not the expert, but I mean,
yes, you're a great researcher.
Professor, I have a question, and thank you very much for your lecture. And based on your lecture, what I understand is SEM is for comparing the observed metrics with the estimated metrics, and at the end it's about the correlations. But some of the papers still out there, some of the researchers, they are also mentioning about the causality with the SEM, and that part is somewhat confusing me, and I would like to ask you about your opinion. Is there and then I was checking on the online about the causality with the SEM, and they are also talk about the causal model with that, and I would like, so that is my question.
Yes, I mean, usually SEM doesn't test causality. SEM tests relationships. SEM doesn't say one thing causes the other. If you want to look at, if you want to figure out if something causing something else, you have to control it for everything. So you need to use experiments. We can only establish a causality using experiments and in a very controlled environment. SEM tests a bigger, gives you a bigger picture. If you want to, it tells you the direction of the relationship. It tells you the magnitude of the relationship, but it cannot tell you if that's causing that relationship, because there might be other variables that are not included in the model, and that the relationship might be caused by those. So you need to run an experiment. Experimental studies are the best to establish a causal relationship. Does it answer your question?
Yes, and then so if I'm not wrong, still, I mean, like some lecturers, they are if they are mentioning about the causality in the SEM, should I understand like the prediction, the direction way?
Yeah, I think that this is based on the relationship. They are talking about the relationship, but we don't know if that thing is causing that effect, because we are not controlling for other things. I mean, if we are collecting data, survey data, then there might be other things that might be affecting the responses. We don't know those things, but with experiment, we can control everything. So we can identify the relationship between A and B with experiments. But with the SEM, that's not really possible. Earlier, when SEM was first introduced, it was introduced as a causal models. If you look at the earlier books, they talk about causal relationships. But later, people start arguing, saying that that's not a causal relationship, it's just a relationship. And experiments, well, some people are still saying causal. I mean, you need to do your own reading and then have your own understanding, but the majority of people now agree that SEM is not a causal model. But there are still a large group of people, they believe that SEM tests causal relationships. But for me, if you ask me the question, you have to do experiments. That's what we do. You start with the SEM, okay, identify the relationships, and then run experiments to test to see if they are caused by, if X is caused by Y. And you can only do that through experiments.
Okay.
Because you have to control more of them.
Professor, I have a question. Can you hear me? Yes.
Yes.
I have a question too, and my question is similar to Chloe's. So actually, when I read the paper, many researchers use when they developed hypothesis, uses the word influence or the effect, some kinds of X positively influence to Y, something like this hypothesis. But as I know, the SEM is quite difficult to figure out the causality, because the SEM is calculated based on the covariance, but many researchers use the influence or the effect. So I'm a little confused as a student, what is exactly different, the influence and the causality, a causal relationship. So could you explain the differences?
If you are, If you are saying causal relationship, that means X causes Y. It's like this. there is a relationship between drinking and accidents, yes?
Yeah.
If you drink, you may get
no.
into an accident.
Yeah.
You may. But
May.
drinking will not cause accidents 100%
Yes, yeah.
of the time.
I see.
But drinking may influence,
Yeah.
may result in an accident. Doesn't happen to everyone. It happens to a small group of people who are drunk and driving. Many drunk drivers don't get into an accident.
Yeah.
But if you are saying there's a causal relationship, it should happen all the time.
Yes, yes.
Drinking should result in accidents.
Yes.
But it only happens what? 1%, 2% of the time. So drinking increases the possibility of getting into an accident, but doesn't cause accident. Not all the time. I think that's the difference.
Oh yes, I understand. So R-square is the R-square means the explanation of the independent variables. So that means not causal relationship, just influence. I mean the correlation, right?
Yes.
Okay, I see.
Because if there is a causal relationship, X should cause Y. Okay. For example, I drink, I drive, I should get into an accident.
Accident, yeah.
That's the cause. If if drinking is the cause of the accident, causing the accident. But I mean, there are some significant, there are some stuff that will cause that relationship. There will be a causal relationship.
Okay, I see. Okay,
but
thank you.
Yeah. I think that's why people are not calling it a causal relationship, because we don't know if that's going to cause that. I mean, if you do a test, if we do this in a lab, in an experiment, with 95% accuracy thing, 0.05, basically that 0.05 tells us that 95% of the time that thing is going to happen. And if we do a test, if we get 100 people drunk, put them in a car, and see what portion of them will get into an accident. 95% of them should get into 95 of them should get into an accident.
Yeah.
Then we will establish a causal relationship. If it's less than 95%, there is no causal relationship. Doesn't make sense.
Okay, I see.
No, it doesn't make sense, because that's why we need experiments. With the experiments, we can see the cause and effect
causal relation. Yeah.
Okay.
Certain, I mean, with a 0.05 certainty. I mean, there will always be errors.
Okay. Other students, we have just 10 minutes left.
I also have a question, Professor.
Sure.
Yeah, thank you for your presentation. This is the first time that I looked at very detailedly about the indexes and how it works. So thank you very much. My question is, once I tried to use the Amos to run my model, and the indexes were not acceptable, and I tried with the same models, same data with the smart PLS, and I got the significant result. So the same model, same data, but sorry.
Did you get different results with Amos?
The Amos, the result was not acceptable. So I tried with the same model and data with the smart PLS, and then I got the significant result with the same, exact same one. So I wondered how it happened. And the next one
with Amos, it's really hard to define the model. Maybe you missed something.
Yeah, I think so. So
when you define the model with Amos, and sometimes Amos can get confusing. And test the same model using M+. Do you have M+, access to M+?
Not yet, but I will try after this.
I think M+ will give you the best results.
Oh, all right.
Because what happens is with smart PLS, you use click the button and then move the things around. You define the relationship with arrows. With the M+, you actually write the code. You tell the software where the relationships, which relationship should be calculated. And then M+ has a more strict, it's very strict default code, and M+ is more strict. So you have a less chance of making a mistake. With Amos, lots of people make mistake. With Smart PLS, I think that lots of people also make a mistake because sometimes they cannot define the relationships.
So can I say like M+ is more like reliable software?
I don't know. M plus is yes.
Yes. Okay. Thank you.
That's what we teach our students. We don't teach Smart PLS or Amos. We have those. We have access, but we want them to know how to. More reliable results, so it's less possibility of making a mistake.
Okay.
Amos, lots of people make mistake. Lots of people.
Yeah,
Okay.
it's really hard to get a result. Yeah. Thank you very much.
But I understandable the question and answer. They're running Amos not acceptable and go to the Smart PLS is acceptable. So that is quite happened to us a lot.
Yes. So I mean, either it's the problem with Amos or Smart PLS. You're supposed to get same results, similar results. I mean, we run stuff on different statistics, and we usually get very similar results. I mean, there are some variances, but not that major.
Yeah. Okay. Other questions?
There might be some other issues. I don't know. I think it might be the specification with the Amos.
Okay. Other questions?
Professor,
Sure.
Okay.
thank you for the passionate lecture today. I want to also ask you about the I-square score. Even though I do not know exactly the meaning of the I-square, but when I read paper, there are many scholars who discuss about the I-square scores. So
I-square or chi-square?
I-square.
I?
R.
R-square. Okay, R-square. Okay, what R-square is? Okay, go ahead. Finish your question.
Yeah, sorry about my pronunciation.
No.
So, Professor, what do you think about which score is the best score and which score is the recommended minimum scores about I-square?
Okay, R-square, basically what that is that's the variance explained in a construct by independent variables. Okay, like if we were talking about drinking and driving and getting into accident, yes? So I will use the same. I think it makes sense to everyone. If you drink and then drive, if 10% of the people gets into an accident, then basically that's 10% of the accidents, okay, are caused by drinking and drive causes 10%. There's a possibility that if you drink and drive, there's a 10% possibility that you will get into an accident. That's like R-square. Okay, but what R-square does is R-square explains the variance in a factor. For example, if we use the drinking and we use the accident thing, okay, there's a 10%. If you drink, there's a 10% possibility you will get into an accident. And also, the rain, when it rains, more people get into accidents. So rain also may increase accident possibility. And there might be some other variables that may cause accidents, or the other drivers, or some other. So that's the combination of those variables explains the possibility of having an accident. And R-square explains that variance. In social sciences, we rarely get very high R-square. This is social sciences because we don't know what causes what most of the time. So there are some guidelines though. Okay, if your R-square is lower than 0.3, okay, basically if less than 30% of the variance is explained by the other independent variables, then that's low R-square. Between 0.3 and 0.7 is mediocre, medium, and then anything higher than 0.7 is high R-square. This is the guideline that usually we use. But in social sciences, if you get anything 0.4, 0.5, I think this is a very good R-square because of the number of variables. And there are lots of things that affects what we do. From from weather to what you eat, from texting. You know, when you drive, people text and then they get into an accident, talking on the phone, trying to figure out which music to listen, playing with the media player in your car. There are lots of things. And,
Okay.
and even the sun, when you drive, sun gets into your eyes, you get into an accident. So that's why.
Thank you.
Those are the guidelines. No problem.
Okay. We have 3 minutes left. Any other question from student side? If not, I have a very important question too.
All right.
Professor Dogan, you are one of the journal editors. These days, when I submitting my paper to the top tier level journals, SCM is not enough to prove my theoretical point of view or research model. So the editors require me to do mixed method analysis to figure out the causality and relationship. So that is one of the, you mentioned just right before, causality and relationship. So we have to get an experiment design for getting a solution. So what do you think about that? The only SCM method or mixed method together? So is this a big trend change at this moment? So as an editor, so what do you think about that?
No, it is changing. Journal laws are getting more strict, more restrictive. But I mean, it's not. Basically, when you write a paper, depending on the topic, depending on how innovative your topic is. If you do something new, something groundbreaking, I mean, method doesn't matter. But depending on the purpose of your research, if your goal is to identify some causal effects, then you may have to use more than one approach. Especially if you are running experiments, you have to run several different experiments for every single relationships. Again, I mean, I think people have different opinion, and nowadays everyone is saying, "Oh, you need to use more than one data set. You need to do that." I mean, using more than one data set is understandable. Using different methods is understandable, but again, it's sometimes it's not possible, depending on your topic. For example, if you are getting data from CEOs, there is no way you can use two data sets. There is a very small group of them. I mean, depending on the purpose of your study, depending on your population, depending on what you are doing, and also depending on the topic. Now, there are very hot topics or something new that no one has done before. Of course, you would have exploratory study because you are doing something new, something different. But if you are working on something well established, then you may need to have more than one studies, or you may have to use multiple approaches. But I mean, more and more journals are requiring more than one data sets, and then more than one testing multiple approaches. But the problem is, at the same time, they are asking you to fit everything into 7,000 words.
Yeah. Okay.
And it's getting harder. We want
Okay.
theory.
Anyway.
Yeah.
Like when you say the different data set converge and different method approach converge, is publication is getting harder and harder at the top tier journal levels.
Yeah, that's true. It's publication, because so many people are trying to publish.
Yes, right.
And then editors they have to come up with some rules, because if you are getting so many papers, which one are you going to publish? So you have to eliminate some of them. But I mean, I don't believe that if you are using one data set, that's a good paper or one type of approach, depending on what you are trying to do.
Okay. Right.
It's a case by case. It should be a case by case approach, rather
That's right.
than a blanket statement.
Okay, Professor Dogan, so our time is up, and I'm greatly thankful to your very great presentation, especially SEM for our master degree students and PhD degree students. They are today overall understanding about the SEM. Absolutely, I will bring you again to our class sooner or later. It's a great lecture.
Thank you. I hope everyone enjoyed it, and I hope everyone learned something, or at least get a main understanding of how this thing is.
Okay. Okay.
Yeah.
So and our students will have interest in your journal as well.
Yeah, sure.
And submitting good paper to your journal as well.
Yeah, you guys keep in touch.
Okay, keep in touch.
Yeah,
Thank you.
Thank you, and you guys enjoy your Friday. Today is Thursday here, so we will.
Okay.
All right, take care, everyone.
Okay. Thank you very much, Dogan.
Thank you. Bye bye.
예, 학생 여러분, 오늘 이제 첫 수업을 했는데 이 수업은 사실 세미나가 초점인데 수업이에요. 그래서 한 장짜리 리포트를 해갖고
All right, bye bye.
시스템에 업로딩 해야 됩니다. 예, 감사합니다. 바이바이.
Thank you.
그래서 이 수업은 내가 그 퀄리티를 측정하지 않아요. 근데 퀀터티를 측정합니다. 그래서 수업은 다 누구한테 오픈돼 있지만 한 장을 또 정리를 해서 서미팅을 하십시오. 그 서미팅을 다 하면 만약 10번 하면 10번 다 하면 A 플러스가 나갈 거예요. 근데 안 하면 그건 캘큘레이션이 돼 갖고 점수가 C가 나갈 수 있어요. 여기 참석을 안 하면. 그러니까 내가 이거를 여러분들한테 좋은 세미나를 제공해 주기 위해서 하는 수업이지 여러분들이 얼마나 스타디를 많이 해갖고 그 시험을 보는 건 아니에요. 그러니까 굉장히 플렉서블한 수업이고 단지 참여를 해서 이런 수업을 많이 듣고 세상에서 어떤 일이 일어나는지 꼭 알기 바라겠습니다. 자, 그리고 주변에 있는 사람들 꼭 수업을 듣도록 하세요. 이런 수업 어디서 듣기 힘듭니다. 예. 그리고 오늘 이런 수업은 사실 여러분들이 다 충분하지 않을 거예요. 이거 공부. 그래서 이 키워드를 들었기 때문에 구글에 가면 충분히 있고 유튜브에도 있고 책에도 보면 다 있습니다. 근데 오늘 도건 교수가 얘기한 건 논문을 쓸 때 처음부터 끝까지 다 포함이 되어야 할 그 내용들입니다. 그래서 꼭 여러분들이 공부를 해서 여러분들 걸로 만들기 바라겠습니다. 알겠죠? 자, 다음 주에는 추석이기 때문에 추석은 안 하고 그 다음 주에는 우리가 마케팅 실험 연구에 대해서 할 겁니다. 이번 주에는 SM, 다음 주는 마케팅 실험 연구. 김정근 교수님께서 해주니까 굉장히 논문 잘 쓰시는 분이니까 또 그때 보도록 하겠습니다. 자, 그럼 추석 연휴 잘 보내시고 다음 주에 뵙도록 하겠습니다. 감사합니다.
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 민성이 오늘 영어 잘하대.